All right, in this lesson, I'm going to title it The Mathematical Structure of Modern Quantum Mechanics, which is definitely much more drama than, it's going to be quite an anticlimax. But the intent here is really to address the question of the use of vectors in particular, but vectors and tensors in quantum mechanics, right? For the What is a Tensor series of lecture, really address the nature of vectors and the nature of tensors in great abstractness and generality. And we leaned on how they applied to general relativity, right? And we got through the whole thing about how we define vector spaces and how we make tensor product spaces, and we had this whole idea about the metric and how the metric in a certain representation, how metrics in key representations. Whoops, wait a minute, what am I doing here? Are tensors, right? And we talked about the significance of the metric and how it's related to the inner product, and how the inner product is something that you add on to a vector space and all of those things. So the question comes up to people, it's like, well, yeah, I don't study general relativity, I study quantum mechanics, which is typical. General relativity is much more esoteric subject than quantum mechanics by a factor of maybe 100, well, 20, right? I mean, for every 20 physicists that know quantum mechanics, you'll probably find one that really has a handle on general relativity. So what about it, right? We definitely know we use vectors in quantum mechanics. So how do we apply what we learned in the what is a tensor series to that? And I guess that's really kind of what I'm going to go for in this series, short series of supplemental lectures. So we'll start by kind of attacking the classical quantum mechanics, right? Notice I put the word modern quantum mechanics here. And the reason I did that is my primary reference, and I'll tell everybody what that is Sakurai in his textbook, which is called, what is his textbook called? I have it right here. Hold on. It's called Modern Quantum Mechanics. And the reason it's modern quantum mechanics is he really goes full force into this vector fundamental structure, right? I would say classical quantum mechanics relies on the notion of the wave function, right? The wave function is where you sort of start and end in the classical quantum mechanics, which is totally equivalent and completely fine, and in fact is probably the best way to learn this. But the wave function, if you really look at the mathematics of everything, it really rests on a foundation associated with vector spaces. And normally we study vector spaces and then we say, oh, we're going to learn, now that we understand our vector space structure of our theory, we're going to create a representation, which is what wave functions kind of are, a representation of those vector space series, and that representation is going to produce our models of reality. Models of reality, right? But I think in this lection, because most people know about quantum mechanics from the wave function study, we'll try to go the other way. We'll start with our wave functions, understand how they can be translated into abstract vector spaces, and then rebuild the whole thing from vector spaces this way. Well, I'm not sure that's the way I'm going to do it. But we could also start by just creating complex vector spaces and then showing how wave functions emerge. I'm not sure which way we'll go, but it really doesn't matter. The point is that the goal of all of this is to connect the What is a Tensor lecture to the to the theories of quantum mechanics and see how that connection is made. And this ought to give you those of you who are paying attention to this series confidence that our analysis of vectors is a very valuable it's very valuable to have a good fundamental understanding of vector spaces and the associated properties. Now, we don't need all of the What is a Tensor lectures to do this. You definitely have to go all the way through dual space, the constructions of tensors, but we don't need the connection. We're not going to talk about vector or tensor fields. So anything after that, which includes the connections, that's all out. And we don't need forms either. So quantum mechanics doesn't use vector or tensor fields. It just uses a single vector space to discuss the whole system. Whereas in general relativity, you need vector and tensor fields and a manifold and all that to make sense. You don't need any of that for quantum mechanics. In some sense, the quantum mechanical analysis is much simpler than the general relativity analysis in that regard. Okay, so let's begin. All right, so we'll start this with a review of the basic postulates of classical quantum mechanics. Classical because we're dealing with wave functions, right? Just this is most textbooks, most good textbooks of the subject really do present quantum mechanics this way. I've kind of organized the postulates in my favorite order, and we're not going to discuss the origin of these postulates. This is what anybody who knows quantum mechanics has got to accept, these facts here. And once you accept these facts and you learn how quantum mechanics works and you solve all the problems and you come back, then you can start asking questions about these facts. But until that happens, there's no if going below these facts before you deeply understand the mathematics and the implications and the calculations and the basic fundamental models generated by quantum mechanics is illogical, and it's really a waste of time. But the first one is we talk about something, we create something called the wave function. We postulate the existence of something called the wave function. If quantum mechanics applies, the wave function of a system exists. And this wave function is a continuously differentiable function of space and time. This is a little spatial vector, time. And that wave function describes the whole system, and any information about the system has to be derivable from this wave function. If there's any information about the system that is not derivable from this wave function, the wave function then must be expanded to include it. It's a fundamental postulate that everything derivable from the system must come from this wave function. The second postulate is that things that can be measured are going to be described in quantum mechanics by operators. Operators which act on wave function. Now, an operator is a mathematical object that takes functions, or, well, it generally takes, the way we're going to use it is it takes functions and returns other functions, right? It changes functions. So operators act on wave functions to generate other wave functions, and all measurements in our theory are going to be, all possible observable things must be assigned operators. And of course this makes perfect sense. If you're going to postulate that everything in quantum mechanics has to be derived from a wave function, right, then certainly if things change in the world, operators you must change wave functions, right? And to adjust wave functions, you need operators, right? So everything is an operator. But the other postulate is that things that we measure in the world, our measurements of things, our possible measurements must be eigenvalues of operators, Now look, this is not the place to go into what an eigenvalue of an operator is. If you don't know what an eigenvalue of an operator is, you're basically in the wrong lecture at this point. I have to assume you know quantum mechanics. The purpose of this lecture is not to teach quantum mechanics, but is to kind of talk about how vectors and tensors find their way into the foundational structure of quantum mechanics. So it's a review of like the fundamentals of quantum mechanics. And if you took a classical class in quantum mechanics, we're going to sort of rebuild the fundamental structure of quantum mechanics using the language of vectors and tensors. So this, you've got to understand what the eigenvalue of an operator is. But of course, an operator acting on a wave function will produce an eigenvalue times the wave function if that wave function is an eigenstate of the operator. And then this value A, this number A, is called the eigenvalue, which can be real or complex depending on the type of operator. Number 3 is the big one, right? Measurement of an observable leaves the system in an eigenstate of the operator. So the wave function of the system after a measurement is going to be an eigenstate of the operator associated with the observable that was measured. So regardless of what the wave function was before the measurement, after the measurement it will be in an eigenstate of the operator associated with the measured observable. This is the big one. This is the one that everybody really has a lot of heartburn over. And the reason is because it's entirely ad hoc. It is entirely ad hoc. It has there's no logic to it that can be derived from any analysis of classical mechanics. There's just, it's totally out of the blue. You can actually show how this idea makes sense from classical thinking, because basically, the way systems evolve in classical mechanics is determined in terms of functions of position, time. In the more advanced classical mechanics, it's done in terms of generalized coordinates and generalized momenta. Observables being operators are a logical extension of how you go from quantum mechanics, from classical to quantum mechanics. You can actually make that connection. But this one you can't make. You have to define a lot of things. First of all, measurement, you have to define. Measurement's even a little bit of a problem here. But this one you can actually assert that there's really not many alternatives for how things can end up being in quantum mechanics. But here, what you're saying is the act of measurement actually changes the system in a very specific way. And the big deal here is that, well, we are the people who decide to make the measurements, and therefore somehow the physics is connected to our decision-making process. But then you can also argue, well, no, nature makes measurements as well, and it just becomes quite a philosophical morass. But as a practical matter, this is a very, very important statement to keep our understanding on track. It's also called as far as interpretations goes, this is called the Copenhagen Interpretation. I won't even try to spell Copenhagen. The Copenhagen Interpretation is sort of buried in number 3. Whenever you hear about collapse of the wave function, right, which is a completely ad hoc idea, that is all buried in number 3. And a lot of work on the foundations of quantum mechanics really rests on attacking number 3, trying to get rid of it. And the many worlds interpretation is the number 1 contender for getting rid of number 3, to eliminate this ad hoc requirement. And then the fourth postulate of quantum mechanics is basically the Schrödinger equation, the time evolution of the wave function. If you leave the wave function alone, it as a function is going to change in time. And, it's a function of time. So, of course, the function is... basically, the Schrödinger equation says that the wave function solves this differential equation, where H is the operator associated with the Hamiltonian of the system. So that's a postulate of quantum mechanics, and actually, in principle, we can get around that as being a postulate. There is something called the time evolution operator, and from an analysis of the time evolution operator, you can justify the Schrödinger equation, so you don't need to make it a postulate. But in the beginning, that's a waste of time because, well, I should be careful. Sakurai does it, so I'm not going to say J.J. Sakurai, the great father of quantum mechanics pedagogy, is wrong. But let's just say that if you're willing to accept the Schrödinger equation, you can learn all of quantum mechanics very quickly. If you're going to start by having to justify the Schrödinger equation, you're going to immediately... have a slowdown in your initial pickup of the subject. There's no harm in assuming this thing and then moving forward and coming back later to derive it. Similar with Maxwell's equations, right? You can spend a lot of time trying to figure out why Maxwell's equations are the way they are, or you can accept them as the analysis of 19th century physics and then learn how to use them, get comfortable with them, own them, and then go back and understand how they came about and why they are what they are. Okay, so these postulates of quantum mechanics are an important thing to keep in mind as we execute our work. All right, so let's begin by talking about our wave function. The wave function is continuous, it is differentiable, and it is complex valued. It is complex valued. So that is, every wave function has at least those properties for the situations that we're going to be dealing with. Now, we also know that if the wave function represents a state of a system, then the same state is represented by any complex number multiplied by that wave function. So a psi of r and t, that's the same state. Just because you multiplied it by a complex number doesn't mean that the state is actually changed, right? So the state, any complex number times psi, r, and t really represents the same information. You're not adding or subtracting any information by multiplying by some arbitrary complex number in the front. So now notice these two are different continuous differential complex valued functions, right? You know, you give on r and t here, you get something different from r and t here by a ratio of a over b. So the functions are different, but they represent the same system. And what we therefore understand is that systems are represented by rays, right? It's a ray that actually represents the system. And that's this concept. If you multiply by a complex number, you're going to get a ray. And we'll come back to that in a moment when we zero in on the vector space nature of all this. So so we have that, and then we also have the fact that you can add wave functions together to get another wave function, right? Because we know, let's see, 0 and 1 equals psi 2r of t. Because if I have a continuous differential complex valued function over a certain range, and I add to it another one, I get a third. So you can add wave functions together, right? You can add wave functions together. And since they are continuous complex valued differentiable functions, I also know that if I multiply this by a complex number, right, I will get that by a complex number. So I also know it's linear in A, right? And A could be -1, right? So I could take A psi plus psi, and I could get that to be A plus 1 psi, and if I choose A to equal -1, which is a complex number, it just happens to be totally real, but it's in the complex number, right? So it's an element of the complex number, so that counts. I get 0. So every psi has an inverse, which we call minus psi, right? So now I have shown essentially that all of the key properties of a vector space are satisfied by our wave functions. And indeed, the wave functions do form a vector space. And the key difference is that A, this multiplicative scalar, which we called in our What is a Tensor lectures, the scalar, is a complex number, right? Scalars are complex numbers, not real. So therefore, this wave functions form a complex vector space. Now notice, it's not a complex vector space because this is a complex valued function. That is irrelevant. It's true, but it's irrelevant. It's complex because the scalars, the bin of scalars, is the bin of complex numbers. I could have had anything here. These could have been real valued. If I change this to real valued, you know, everything's totally different, right? Real valued functions are not even close to being the same as complex valued functions. But that wouldn't change the fact that it's a complex vector space. So the takeaway here is wave functions form a complex vector space. Okay, so now that we've decided that we can create sets of wave functions that satisfy the general properties of a vector space, we're going to add a few more properties to this set in order to create the real thing we want, which is called a Hilbert space. A Hilbert space is a vector space, but it's a little bit more. In particular, it has an inner product. And set with an inner product is now an inner product space. So we need to promote our average vector space to an inner product space. So if we can imagine two, I'll drop I'm going to drop these arguments now. If we imagine two different vectors in our vector space of wave functions, and we want to form the inner product, we're going to create the following definition for the inner product. It's going to be some definite integral, and This definite integral will have boundaries, a and b. Those boundaries could be minus infinity to infinity. They could be 0 to L, minus L to L, where L is some distance. Whatever the boundaries are, they're fixed for the inner product. You set B, you set A, and that's the inner product boundaries for all inner products in the Hilbert space. It's not some variable. It's not a parameter. It's defined for the Hilbert space. But so if we're going to create an inner product for this set, which I guess maybe I'll call V, just to name it after something from the old What is a Tensor lectures, then this set V has this inner product. And if these are the two vectors for which I want to find the inner product, this was the old notation for the inner product, I'm going to take the first one, which is a function. I'm going to take its complex conjugate, and then I'm going to take the second one and multiply the two, and do so, and then take this integral for the purposes of this this demonstration. We'll just consider these to be one-dimensional functions. So this R will now become just an X for now, which is how we learn it in elementary quantum mechanics, which I'm trying to sort of refresh anyway. And once you have the inner product idea, then of course you have the norm idea, where the inner product of any member of any wave function with itself is going to be a to b psi star psi dx. Now this will generally be a complex number, but this will always be a real number. So, and this is defined as the norm of psi. I think it's actually wait. It's the norm squared. This is the norm squared. Well, it's the square norm of psi, and that will be a real number. So we want this feature that the norm, when we calculate the norm of a member of our space, we get a real number. It's just a convenience. And with that, we're almost at all the requirements for a Hilbert space. The Hilbert space, we've got the fact that it's a vector space. We've already figured that out. We've given it an inner product. We like this inner product, so that's the inner product of a Hilbert space. And once we have an inner product and we can define a norm, then I can talk about a sequence, say phi n minus psi m, right? So I can take the difference of a sequence of vectors phi and of vectors psi. I can take their difference, and then I can find the norm of that difference. And if the norm of that difference goes to 0 as n and m go to infinity, then the sequence is called Cauchy. Right? A Cauchy sequence is such that it has this property that the difference between these two vectors gets smaller and smaller and smaller for higher n and m. And if every sequence like that would exist, where these guys here are members of the vector space, we can find Cauchy sequences that go to 0. The point is that this difference, as m and m go to infinity, right? This difference must converge to another. Ultimately, this difference here, if it satisfies this Cauchy principle, must converge to a wave function that is in the, let's call it omega, a wave function that is in the Hilbert space. This is a topological property. It's called completeness. So Hilbert space have to be complete. And with those properties, you do have a Hilbert space. The Hilbert space is a vector space, check. It's an inner product space, and this is our inner product definition. And it is complete in the sense that all Cauchy sequences converge to a member of the Hilbert space. And when you have that, you got a Hilbert space. All right, and as a reminder, we'll build two very famous Hilbert spaces. One is called, I think, H1. And H1 is the set of all wave functions that satisfy the property that they're defined between 0 and L, and the norm of the wave function is finite, right? So this is supposed to mean the set of all wave functions defined between 0 and L such that the norm is finite. That will be a Hilbert space. If you take any two functions of the set, add them together, you'll get another function of the set. All the Cauchy sequences converge. It's an inner product space because of the definition. It's a very famous Hilbert space. Another famous Hilbert space is, the way I learned it, was called H2. And it was the set of all wave functions such that for the entire real line, the norm is less than, or is finite, right? The norm is finite. So these are defined very similarly, but in the sense that it's defined in the sense that we're looking for things with finite norms on certain intervals. But this one is the whole X line. I think this is called L squared space often, as opposed to just L space, or just H1. And now that we have this idea of the Hilbert space, I want to remind you that any complex number times any wave function produces a model of the same physical state. So that means that this object represents a physical state regardless of the value of A. And so the physical states are now considered as rays in Hilbert space. Right? So the physical states aren't modeled by vectors in Hilbert space. They're modeled by rays in Hilbert space. Now, every vector space has rays, right? If I go to the classic stuff that we were doing before, and I said, okay, I have a basis, En. We haven't talked about the basis of Hilbert spaces, but say I have the basis of an n-dimensional vector space, En, and then I have some vector that I might write as Ai, Ei. Well, that's a single vector in the vector space, the n-dimensional vector space. But then I could say, well, I can multiply this by some number, say h, and if I accept all of the vectors that could be represented this way, then I have a ray in the vector space, finite dimensional or not, right? Ray in vector space. And so now it turns out that rays themselves may or may not model things physically, depending on what I'm kind of working with. But in the context of quantum mechanics, the state of a system is modeled by a full-sized ray in the Hilbert space. All right, so now that we have our concept of a norm, I can definitely consider the idea of orthogonality, because I would just write phi star n phi m dx from A to B, and that has to simply equal 0. And if that's the case, then I know phi n and phi m are orthogonal. And if, furthermore, if I set it up so that all of the phi n's, whatever n is, if I set it up so that the norm of that, the norm of that is equal to 1, then I have orthonormality. So we can with this inner product, we can define orthonormality. Now, there is a lot of problems because of the fact that we have an infinite basis. And these are subtle mathematical problems that are definitely glossed over in most introductions to quantum mechanics. And that's not really a big deal. I mean, it's not even like I've known physicists who've been involved in this study for their entire careers, and they've never gone back to sort of unpeel the mathematical issues of infinite number or infinite dimensional vector spaces. But let's just say that there's two different kinds of circumstances for basis vectors. First of all, let's imagine an orthonormal basis system. What would we mean by that? Well, we would mean that any wave function psi can be written as I equals, say, 0 to infinity of ai phi I, where I is this sort of orthonormal basis system. And if you can do that, we're going to call this a Hilbert state basis. Is it technically a basis of a vector space? Well, not necessarily. There could be, the problem is that we're saying that this sum does not have to terminate, and it frequently will not terminate. And strictly speaking, the way we want to define basis vectors even in infinite dimensional vector spaces is that everything should be defined through a terminating sum of some kind. But we're okay with that. This is going to be called a basis under this circumstance. These guys, phi n, will be a basis if any member of our Hilbert space can be written this way. Alternatively, there are circumstances, this would work for H1. This would work for H1, but it would not work for H2, because H2, there's just a lot more, there's just many more, where's my H2? There's many more vectors allowable in H2 than in H1, and we can no longer have a countable, the whole principle here is that this is countable, a countable sum. So it may also be the case that our orthonormal vectors. So now let's quickly talk about a basis set. Considering, say, H1, we will look for an infinite sequence of functions, an infinite list of functions phi n, and we want it so that phi n phi m is equal to, well, we want it to be orthonormal, so it'll be delta n m, right? And if that's the case, if we can find that list, we are going to identify that as a basis if every function in the set can always be written as the sum, I equals, I'll start from 1 to infinity, of some constant, when I say constant, I'm thinking of a complex number, times phi sub I. And that will mean that this set of all these phi n's is what we're going to call a Hilbert space basis for H1. And notice in this case we are doing it as an infinite sum because we have what we're considering to be a countable basis. And as a reminder, it turns out for H2 such a countable set is not possible. So we change this notion of basis such that any function, say of space dimension x, can be written as a infinite integral from minus infinity to infinity of some spectral function, which we'll call, I guess we'll call it k. I think usually it's called k. The basis set is going to be also indexed with k, the spectral function. It's a function of x, but the integration is going to be over dk. So the idea here is we're summing over I, but now because this is countable, you can get away with it. But if you have an uncountable one, you've got to actually integrate over this index dk. So most of the problems that we deal with in elementary quantum mechanics are of this form, and not all by a long shot, but many are of this form. Where the square well potential, the hydrogen atom, where you basically can create this countable series, this countable set of basis vectors. But once you deal with continuous spectra, the basis is defined this way. Now, there are some technical questions about the nature of a basis in a vector space, and if you really dive into the pure mathematics of vector spaces, these things that we use in physics that we're going to call a basis, there's some issues. Don't worry about those issues. Just accept these two kinds of definitions of a basis. This is a basis for a continuous spectrum. This is a basis for a discrete spectrum. All right, so how do basis vectors work in our two Hilbert spaces, H1 and H2? Well, in H1, a basis vector, if I have a vector inside the Hilbert space and a wave function inside the Hilbert space, I want to be able to express that as the sum of a series of wave functions like so. And if I can do this, then the set of psi n we're going to call a basis. And so notice this is an infinite sum, right? This is an infinite sum, and any wave function inside H1 should be expressible as this infinite sum. And if I can find a set like this, then I will call that set I will call that set a basis. Let me make it a little. Now, for H2, it's trickier because in H2 I have to be able to write it as an infinite integral of a spectral function times a wave function, and this is over dk. And this can be really confusing, right? But it's really the same thing. This is a complex number as a function of k. This is an uncountable number of basis functions, so that's why we have to actually execute this integration. Here we have this discrete sum, here we have a full integration. So it turns out that any element of H2, these square integrable functions over the entire real line, ultimately looks like this with an integral, and H1, which is only over a finite section of things, looks like this. It's a discrete list. Now, there's some problems here with the idea of the mathematician's definition of a basis of a vector space. And it has to do with the fact that you have an infinitely large basis. And also that you're allowing this infinite sum to exist. In other words, I'm accepting an infinite sum to represent ultimately any vector. And mathematicians like their vector spaces to have finite sums. So so physicists have stretched this definition a little bit, and these are considered the bases of Hilbert space. This is a basis of a Hilbert space where we are dealing with a continuous parameter k, and here it's a discrete parameter n. Just to exemplify the second one, which is a little confusing, I'm going to define this sort of the standard. I'll show you how this sort of becomes a limit of this guy in a sense. So we'll define our standard basis vector. Remember, the basis vector is a function of x, right? And we'll go with 1 over the square root of L times e to the I kx, right? So the k down here, which is sort of the index of the basis vector, shows up as the coefficient of e up there, and it's a function of x, and there's the functional dependence on x. L is some length, is some discrete length on the real line. Now, if we treated this, and we looked at the inner product of this, and we're trying to show, okay, is it normalized, for example? We would go phi k of x, phi k of x, and we would write an integral minus L over 2 to L over 2, and we would put the complex conjugate here, so it'd be 1 over the square root of L e to the minus I kx times 1 over the square root of L e to the I kx. And this integral, it's an inner product, right? The inner product integral is defined in terms of x, right? This is not the expansion integral, which is done in terms of k, right? This is just the inner product. I'm trying to show that these two are, that this set of basis vectors is going to be orthonormal, and so right now I'm worried about the normality. So I take k and k are the same, so k and k are the same, so those cancel out, so I end up with 1 over L times the integral from minus L over 2 to L over 2 of dx, which is 1 over L times L over 2 minus L over times L, which equals 1. And now notice, in the limit that L goes to infinity, where this does become minus infinity to plus infinity, which is the definition of the inner product for our Hilbert space, for H2, the H2 inner product. Where did I write that down? The H2's inner product goes from, where did I oh, here it is. The inner product for H2 goes from infinity to minus infinity. So nothing here is affected by that. I just take the limit as L goes to infinity. So these are always normalized to 1. Are they orthonormal, however? So the way to figure that out is I have to take two different ones, right? Phi k prime and phi k, where I'll suppress the x, the inner product there is going to be the integral minus L over 2 to L over 2, 1 over square root L e to the minus I k prime x, 1 over square root of L e to the I k of x, dx, and this will equal 1 over L times the integral from minus L over 2 to L over 2 of e to the I k minus k prime of x dx, which is 1 over, which in the limit as L goes to infinity, is 1 over L times the Dirac delta function k minus k prime, which equals Dirac delta function k minus k prime, which equals 0 if k does not equal k prime, and equals unity if it does. If it does equals unity, then these limits of integration will interact with the L to give you 1. So it's orthonormal. So these are examples of functions that are the basis of H2. And of course, because of the way they appear, you can see how it all has to do with, it's really the Fourier expansion of arbitrary functions in H2. So that's just a quick refresher on the basis vectors of our Hilbert space. All right, now the next thing is operators. Operators are the objects that model the physics of our system, and operators must act on wave functions to give other wave functions. So if I call an operator A, which is not uncommon to give it a little hat, and I take that operator A, it's going to change function. So I provided a wave function, which I'll just do it this way. I should get another wave function back, right? I should get some other wave function back. Operators change wave functions. And in particular, operators can, there's no particular definition for an operator. Anything that satisfies this kind of property, you feed it something from the Hilbert space and you get something back from the Hilbert space, then that operator can work with our problem. So a pretty classic example of an operator is, say, the partial derivative with respect to one particular direction, x. You could imagine a whole variety of differential operators that could be of arbitrary power and sign with coefficients. So I could create a differential operator, say p hat, that was d by dx partial x by partial xy times 5 plus 6 partial squared partial x squared plus 2 partial y plus 5, right? And then I take b, I can feed it a function, and I will get another function. I'll get some other function. So that would count as an operator. Another operator might be an integral from 0 to 5 with respect to one particular direction. That could be an operator. We could just divide a function by 5. I could say the operator h acting on psi is psi divided by 5 if I wanted to. So the job is, so operators can be very, very broad objects. The trick is to find the ones that matter to physics the most. And of course the ones that are famously so is the momentum operator, which is minus I h bar partial by part. That will be the momentum in the, say, the x direction. The general momentum operator is minus I h bar times the gradient, which is a vector. So that's the famous one. So the question might immediately come up is, well, how do I know what operators are corresponding to what physical observables? And that's something we're not going to cover here. This can be understood as the generator of translations through an understanding of the translation operator on a wave function, and this being the generator of translations, you can link it up to the momentum operator without much trouble. The energy operator is, or the Hamiltonian. In quantum mechanics, we call it the Hamiltonian, but we treat it like the energy operator. And that's the momentum operator squared over 2m. is your plus some potential, which is usually a function of position. So this operator is critical because it shows up in the Schrodinger equation, of course. But the point is now we need a whole bunch of operators out there in the world to act on wave functions. So as a reminder, that's the next, it's part of the postulates, is understanding these operators. Now once we have these operators, we've defined the idea of an expectation value of an operator. The expectation value is going to be that integral from a to b. It's really this inner product, right, of some wave function. You have to have a state, right? Then the operator acts on the state, and you integrate over, I guess we'll integrate over space, right? So we're imagining that our wave function is a function of space and time, and the expectation value is pretty simple to understand. You take the operator and you act on the wave function, and then you take the inner product of the wave function with the wave function acted upon by the operator, and that inner product gives you the expectation value, the so-called expectation value of the operator. So that's something we have to remember from elementary quantum mechanics. And then we understood and defined the Hermitian adjoint of an operator. So if I have an operator A hat, the Hermitian adjoint is A hat with a little cross there. And that's defined so that the expectation value of the operator is equal to this guy, right? The adjoint is such that if I flipped positions in this inner product, I would get the same answer. So I'm basically saying that psi star A hat psi dr equals the integral of A adjoint psi complex conjugate acting on psi dr. And of particular interest are the circumstances when an operator is self-adjoint, right? When A equals A adjoint, and those operators are called Hermitian. And Hermitian operators are critical, and they have a couple important properties to track. And let's review those right away. So we will start with considering our operator A. We'll start with its action on its own eigenvector, right? So if we define phi n, the set of phi n are the eigenvectors of A, then we know that A acting on its own eigenvector is going to return a complex number times the eigenvector itself, right? It stays on the ray, in other words. It changes it, but it remains on the ray. It doesn't really change the physical state if phi n is an eigenvector. So how do we, so what's the significance of this? Well, if it's a Hermitian, if it is a Hermitian operator, then we would expect that phi n, A phi n, to equal A phi n phi n, like this. And of course, on this side, what do we end up with? We end up with the integral of phi n conjugate A phi n, and then we'll go dr, and that's got to equal the integral of A phi n conjugate phi n dr. And this side here is going to equal phi n conjugate A phi n dr, which is going to equal I now substitute this for A phi n conjugate phi n dr. Let's see if I can keep going here. This becomes A times the integral of phi n dr, and this becomes the integral of A conjugate integral phi n conjugate phi n dr. And of course, this and this are the same, so I end up with A equals A conjugate, which means A is a real number. So what we've basically shown is that if I have a Hermitian operator, Hermitian, and that was Hermitian because I made this statement, I know that its eigenvalues are real. That's not true if it's not Hermitian. If I can't assemble this statement here, then none of these equalities follow, and A does not have to equal A conjugate. So that's one critical property, and we've shown it using the wave mechanics inner product function. All right, the next quick thing that we should definitely think about is the following inner product, an eigenvector of a Hermitian operator A. Oops, so we have a Hermitian operator A, one eigenvector, and then we have the Hermitian operator acting on a second eigenvector. And because it's Hermitian, we want to compare this with phi n, phi m. Right? This equality is established only because A is Hermitian, only because A equals A adjoint, right? And we just follow the exact same logic we did before. In fact, we can accelerate this by just making our substitutions right here, right now. So I go phi n, A m, phi m, right? And I know A is real, right? Because we just proved that A is real. This is A n phi m. And because of the linearity of everything, the way we define the inner product was with an integral. And you remember the integral, it'll go from A to B, phi star, psi star. So, or phi, not psi star, phi star, psi dr. And so, multiplying by a constant here will just come right out. So it's the inner product is linear is the whole point of all that. Let me erase that real quick. And so with this, I can immediately write A n phi m equals, this is A m equals A n phi m. So I write A m minus A n times phi n phi m equals 0. For different values, if n does not equal m, then there's no reason for this to be 0. Eigenvalues don't have to be the same. They can be the same, but they don't have to be. Therefore, this must always be 0 when n does not equal m to force that to be 0. And then when n equals m, when n equals m, then we know the front part is 0. So it's always, so the point is it's always orthonormal. So, or orthogonal. It's always orthogonal. So the eigenvectors of Hermitian operators, are orthogonal. That means the inner product between any two eigenvectors will be 0 unless the two eigenvectors are the same eigenvector. The Hermitianness was established right here in the first line, and we use the property that Hermitian eigenvalues are real numbers down here because we took the difference when they're equal to be the same. Okay, so that's the other important part about Hermitian operators. Okay, so now we have reviewed enough of the classical quantum mechanics structure so that next time we can actually redo everything we just did, but in terms of the abstract notion of vectors. All right, we're going to use the vector in tensor ultimately it's what's called Dirac notation, but we're going to link what we just did to Dirac notation and link all of that to our elementary ideas of vectors and tensors that we learned in the What is a Tensor series. Okay, so we'll talk later.